Grade 12 College Prep Physics. Looking in mechanical systems, our second video, we're looking at friction. And I'm going to break this note up into two videos, which you may or may not watch all at once. That's up to you, just because it's long and this stuff is, it's some of the more challenging stuff, I think, of the course is really getting a handle on friction, especially the calculations with friction. I think everyone has an idea of what friction is. It's the force that no matter what motion happens, it opposes it, right? So, most friction I think of as sliding friction. That's two objects rubbing against each other. There's friction when objects are rolling, and then there's drag, air resistance. We talk a bit about drag later in the course, but mostly what we study is what I call sliding friction, right? Just like whatever force is going to cause this polar bear to come to a stop eventually. That would be friction. Friction, of course, is really a kind of a neat concept because it's so inherent in every process that exists. Like if you think about when Sir Isaac Newton first sort of realized in what we call his first law of motion is inertia, right? And even though I think the idea of an object at rest will stay at rest, an object in motion will stay in motion unless there's an outside force, is pretty inherent in our belief and our understanding of things. But back then, if you think about it, anything you've ever seen moving eventually comes to a stop. Nothing stays in motion, right? You slide something down the hall, it always comes to a stop. And that, of course, is because of friction. Friction is part of every single process that exists. If it wasn't, then there'd be all kinds of awesome, perpetual motion machines that could be developed. But because there's always friction, even the best engineered systems have some friction, right? It's like, it makes us have to work for everything. Kind of a neat idea. What if there was no friction? And of course, that's a huge field of study because of energy, and even friction in electrical resistance is a huge idea. And if you've ever heard the term superconductor, right? Trying to figure out materials that could carry electricity with the least amount of friction, right? You can save a lot of money because friction usually leads to just wasted energy. Anyway. Friction. So the main thing about it, it's always in the opposite direction. So this little picture is supposed to say, okay, here I am forcing something to move, and it's moving this way. Well, if I'm moving this way, the friction is in the opposite direction. Doesn't matter what the net force is or anything. If something's moving west, the friction is east, 100% of the time. Okay? If something's moving up, the friction is down. So we split friction up into two types, sliding friction up into two types. There's what we call static friction and what we call kinetic friction. Kinetic means moving, and static friction's like, I don't know if you've ever noticed when you try to if you try to get something really heavy to push it, right? And it always takes like a ton of energy just to get it started, but once you get it started and it starts to move, then it's a little bit easier. And that really is the difference between static friction. That's that bit you need to just get it started. And kinetic friction is the force you need to sort of keep it at a constant speed, just moving along. So, kinetic friction, force needed to come to keep a sliding object moving. So it's not really it just means that if I want to get if I want to go at constant velocity, if the frictional force is 100 newtons, I need to apply 100 newtons to keep it going constant velocity. If I apply 80 newtons, then I'll start to slow down. I might be pushing, but I'm not pushing enough to overcome friction, so I'm going to slow down and eventually come to a stop. And again, static friction is just that little bit, just to get something going. And almost always static is greater than kinetic. I don't like to use an absolute like always, but usually. Okay, so there's two things that affect the amount of friction between two surfaces, because we're talking about surfaces. Sliding friction means they might be two of the same surface, but there's always two surfaces. And one is the normal force, because if you're really pressing down on something, right, and of course the normal force is perpendicular to friction, or to motion, but you're pushing down on something, and then you want to push it to move it. It's harder, right? There's more pressure between those surfaces. Whereas if you pull up a little bit on something and then try to push it sideways, it moves easier, less normal force. And then the second thing that affects, the amount of friction is just what the surfaces are, right? Obviously. So if you had, you know, I meant to write rubber there. If you had your rubber-soled shoes on and you're walking across ice, you're sliding like crazy, right? Your normal force, so to speak, would be the same. But then you get onto concrete, you're not sliding anymore because same shoes, but the surfaces are different. So the amount of friction depends on what the two surfaces are and how much pressure between those surfaces. There's the equation for friction, and it looks a little funny. N is normal force. Makes sense. I said two things. Two things affected friction. Well, one of those things is normal force, the amount of pressure between the surfaces. And this little thing is called mu. It's called the coefficient of friction, and it's a Greek letter called mu. And so mu is a number that exists, and you can look them up in tables, or you can figure it out in labs, and you will be doing that between your shoe and the lab bench. But mu is a number that represents how much, how sticky the surfaces are. So for example, well, I think we're going to get into that more later, but that's the equation. So there's the coefficient of friction. So it's a measure of stickiness. It's always a number between 0 and 1. So, because it's just a relative thing, and there's no units. It's just like 0.6 or 0.2 or 0.1. And yeah, any two surfaces would have a different value of mu. I think the kitty, which one falls first off the roof? The one with the lowest mu, because a lower number means less sticky, more slippery. So where ice might be like, rubber and ice might be 0.05, rubber and concrete might be 0.8, right? A smaller number means more slippery. So here's just a table of coefficients of friction, and I just pinched that off the internet. And the truth is, these tables exist anywhere, and they're important when you're designing something, because when you, obviously a number that has higher numbers here, there's more friction, more energy lost, right? And sometimes that is what it has to be, because you need a certain material. So if we just look at this for a little bit, first of all, this column refers to what we call the static friction. So this is how we take into account that little bit extra you need to get something started. And then this number here, mu k, is that constant speed, or moving anyway. It's the friction when something's moving. So if we look at different numbers, you can generally see, is it always the case? See, not always, here they're not, here static and kinetic are the same. But in this table, every single time the static friction is greater. By the way, see this? Very rough surfaces at 1.5. So the 1 isn't an absolute thing, but you're going to calculate some coefficient of friction and you'll see. But generally it's between 0 and 1. So nice to see that the friction between our joints, is pretty low. That's good. Ice on ice, 0.03, but something with a lot of friction, steel on steel would have a lot of friction, rubber on concrete, 0.8. Right? Does it have rubber on ice? No. But anyways, you could just Google it, and you could find any, like, these are just constants that exist. Now, the thing is, like a particular sample of, say, rubber or something like that, like one running shoe and another running shoe might have different coefficients of friction between that and a gym floor, right? Okay, so let's do an example. This is the last thing I'm going to do on this note, is this one example, and then we're going to move on. I'm going to stop the tape just because it gets pretty long. Friction's a big topic. So in this example, Ferd applies a force of 300 newtons horizontally in order to pull Ferdette and Dreff, who are on a sleigh. So Ferdette's mass is 40, Dreff's is 55, and the sleigh is a mass of 6. So he might be, yeah, he's pulling this sleigh. The sleigh is waxed wood, and he is pulling across dry snow. So this is just very specific, so I could look it up on the table. I'm going to look up the mu. So first, draw a free body diagram, find the normal force, find the coefficient of static, and find out if he's pulling with 300 newtons, is that enough to get the thing going? Okay? And what I'm saying is, if this force of static friction is greater than 300, then he's not giving enough force. But we'll see. So, first of all, the free body diagram. Here we go. So there's the sleigh. Got gravity down, normal up. There's Ferd's pulling of 300 newtons. And the question is, what is Fs? So there's our free body diagram. And then we want to find the normal force. So the normal force will just be the idea, remember, with normal force is it's force of gravity. So we're going to use the combined masses, right? So we had Ferdette, Dref, and the sleigh. So you use all of their masses in one. So the total mass times 9.8. So there's the normal force. For finding the coefficient of friction, I'm just going to go back a few steps here. What did we say? Waxed wood on dry snow. And it was static, so it must be 0.1. Except I think I put down 0.15. Yeah, I did. Darn it. Should be 0.1, right? So, right, waxed wood and dry snow. Let's just check that again. Waxed wood, dry snow. Yeah, 0.1. That was dumb. Oh well, I'll have to redo my calculation. Good thing it's 0.1, so it's an easy number to work with. So when I calculate my force of friction, don't go copying this because I screwed up. When you calculate your force of friction, then the force of friction that he needs to be applying something greater than to get this thing going is going to be mu times the normal force. So the mu you get from the table, and if something I gave you a question where you couldn't, I'd either give it to you in the question or maybe you could look it up somewhere, but I'll change this number. So 0.1 times that, I guess it would be it'd be 98.9 newtons, or I'm just going to say 99 newtons. So he has to apply at least 99 newtons to get this thing going. So his 300 newtons is plenty. Okay? So that's doing a simple force calculation related to, or not that simple. It's pretty hard actually, isn't it? Force of friction's hard. But anyways, I'm going to stop the video there and we'll pick up on the next one just because this one's going to get really long.